All right, we have come to our final section in Chapter 7. And I think, in my opinion, this is one of the most important topics we do all semester. We're really going to get into statistical inference. And remember that statistical inference means you're taking information about a sample and you're making some sort of generalization to a population, making some estimates about what you think would be true for a population. And so what we're going to do here is we're going to use the central limit theorem to construct what we call a confidence interval. Confidence interval. And so that's what we're looking at in this section, are confidence intervals. So we now focus on inferential statistics, or statistical inference, same thing. Often it is easy to calculate statistics from a sample. We can always calculate statistics based on our sample. That's easy because the sample is right in front of us. But it's difficult and often impossible to calculate parameters from a population. So remember, what we do is we take that sample and we use information about that sample to make generalizations to a population. And that's what a confidence interval is going to tell us. So let's look at an example of where we would use this. It says, according to Pew Research, an October 2016 article indicated that 685 out of 1,201 adults randomly surveyed favor the legalization of marijuana. So the question says, what percent of the adults surveyed supported the requirement to legalize marijuana? So basically they're asking us for p hat, right? So p hat is the proportion of the people in my sample who said they support this. So that would be 685 out of 1,201. And let's go ahead and make that into a percentage. So we're going to do 685 divided by 1,201. And I'm getting about 57%. So about 57% is my p hat. Is that value a sample statistics or a population parameter? Well, it's a measurement on the sample. Therefore, it has to be a statistic. Remember, p hat, of course, is a measurement on your sample. That's always a statistic. Do you know the percentage of all American adults, or P, in other words, that support the legalization of marijuana? No, there's no way for me to know that because there's no way for me to go around and ask every single American whether or not they support this legalization. So my only option is to estimate it based on my sample statistic. So the question says, do you think the percent of adults surveyed who support the requirement is exactly equal to the percent of all Americans who support the requirement? In other words, is our sample proportion exactly equal to the population proportion P? No, it's not going to be exactly equal to, but it should be pretty close. How do I know it should be pretty close? Because this was a random sample and it was a large sample. We surveyed 1,201 adults. That's a pretty large sample. So it's not going to necessarily be the same as the population, but it should be pretty close. It should give us a pretty good estimate. So it says, from the previous sections, we know the following facts. Our estimator p hat, remember we called that an unbiased estimate of the population parameter p because we're doing a random sample. Therefore, the population parameter p should be very close to the sample statistic p hat. Our standard error is going to be the square root of, actually, let me back up for 1 second. I'm going to give you a formula here. Well, let me back up. Our standard error in the previous section, remember, was p times 1 minus p divided by n. And you may not remember, I mentioned in the previous section, but I said we'll talk about it in the next section, that if you don't know what p is, when you have an unbiased estimator of p hat like we do here, we can substitute p hat instead of p. So instead of p, let's go ahead and use p hat to calculate our standard error. And we can do that because we're using an unbiased estimate. So I'm going to go ahead and use the 57% that we calculated earlier. So 0.57 times 1 minus 0.57 divided by our n, which was 1,201. And if we put that into our calculator, 1 minus 0.57 times 0.57 again, divided by 1,201. And then, of course, remember to take the square root. I'm getting about 0.014, it looks like. So about 0.014. 0.014 is going to be the standard error that we use. This is actually called the estimated standard error, but don't get too hung up in the notation. What I want you to focus on is that it's the same basic formula that we used in the previous section. We just substitute p hat when we don't know what p is. Since the sample size is large, the probability distribution of p hat is going to be approximately, the central limit theorem applies here, so when the central limit theorem applies, we know that we're going to have a normal distribution. It's going to be approximately normal, and it's going to be centered around the true population proportion. So it's going to be normal with a mean of the true population proportion, which right now we're estimating to be around that 57%. And we know that the standard deviation is going to be whatever the standard error is that we just calculated, 0.014. There's a 95% chance that p hat is within how many standard errors of the population proportion. Remember what the empirical rule tells you. There's a 95% chance that your p hat is going to be within how many standard errors of the true population proportion? 2 standard errors. So it says 2 standard errors. So in this case, 2 times the standard error that I calculated up here, 0.014, is going to be about 0.028, is going to be 2 standard errors away from the population proportion. Therefore, we are 95% confident that the value of the true population proportion is within 0.028 percentage points of the 57% that we estimated from our sample earlier. This is what a confidence interval is. It's literally an interval of numbers that gives us a range of what we think is true for our population proportion. So we are 95% confident that the population proportion, or the proportion of all American adults who support legalizing marijuana, is between what 2 numbers? So I need a boundary point. So if p hat was 57%, then what I need you to do is take this number, this 0.028 number, and I want you to subtract that. So we need a lower bound and an upper bound. We're going to take that 0.028 number and we're going to subtract it from 0.57 to get the lower bound. So our lower bound is going to be 0.57 minus the 0.028 number. So let's calculate that to get our lower bound. So 0.57 minus 0.028, and I'm getting 0.542. So that's our lower bound, 0.542. And then our upper bound, we're going to do the same thing, but instead of subtracting it, we're going to add it. So we're going to do 0.57 plus 0.028 to get our upper bound. Let's take a look at that. So 0.57 plus 0.028, I'm getting 0.598. So our upper bound is 0.598. So this is our confidence interval. We think that we are 95% confident, we are 95% sure that the true population proportion, or the proportion of all Americans who support legalizing marijuana, is somewhere between about 54.2% and about 59.8%. That's our confidence interval. So an interval is literally what it is. We've got a lower bound and an upper bound that we think is true for our population proportion. So confidence intervals provide us with what? So some little bit of definition here. Confidence intervals provide us with a range of plausible values for a population parameter. The difference in this section, the big difference from the previous sections, is that we don't know what our population parameter is. We're having to estimate it. And so the confidence interval gives us a range of plausible or realistic values that would make sense for our population parameter. A confidence level, which expresses our level of confidence that the interval contains the true population proportion. So our confidence level is how confident are we? How good do we feel about this estimation? In the previous example, our confidence level was the 95%. Now, we can have different confidence levels. We can have a 90% confidence interval. We can have an 80% confidence interval. We'll talk about that in just a minute. But that gives us an idea of how sure we are with our estimate. How good is our estimate? It tells us how often the estimation is successful. If we were to repeat this estimation, if we were to pull sample after sample after sample using the same methods of the same sample size, 95% of the time, for example, we would expect that our sample would actually capture the true population proportion. So it gives us an idea of how good our estimate is. And then finally, it measures the success rate of the method. And this is what I mean. If we were to repeat this over and over and over again, if we were to keep pulling sample after sample from this population using the same method, how good are we? How good is our estimate? And that's what we're looking at when we do a confidence interval. Our margin of error. So let's talk a little bit more about how we actually build that confidence interval. Our confidence interval is built on the margin of error. Now, we actually calculated the margin of error up here. The margin of error was this 0.028 number, but let's talk a little bit more about what we mean by that. So the margin of error is always going to be computed using this funny looking formula, and we're going to call it Z star times the standard error. So Z star is a number that tells us how many standard errors to include in our margin of error. In the last example, we went out 2 standard errors. So our Z star value in that last example would have been 2. From the empirical rule, so the standard error, or the margin of error rather, the Z star values that we're using are based directly on our empirical rule. So a Z star value would correspond with 1 standard error away. So if you remember from the empirical rule, 1 standard deviation away from the mean, that always corresponded to 68%. So that would, and we talk about confidence intervals, that would correspond to a 68% confidence level. Z star value of 2 would correspond with a confidence level of 95%. This comes directly from the empirical. 1 standard deviation out, 1 standard error out, Z star value of 1, 68% confident. 2 standard errors are out, Z star value of 2, 95% confident. 3 standard errors out, or Z star value of 3, corresponds with a confidence level of 99.7%. All right. Let's be a little bit more thorough about this. Let me give you a table of some different Z star values and their corresponding confidence. So some of these we've already done. I'm kind of jumping around a little bit. 95% I'm going to put here in the table. So a 95% confidence level corresponds to 2 standard errors or a Z star value of 2. 99.7% confidence would be 3 standard errors with a Z star value of 3. Now, a few others that may come up. These still come from, I don't want to say the empirical rule, but they come from that normal distribution and how much of that normal distribution is getting shaded. 80%, if we were doing an 80% confidence level, that would correspond to a Z star value of 1.28, which would be 1.28 standard errors included. A 90% confidence level would correspond to a Z star value of 1.645 or 1.645 standard errors. And then a 99% confidence interval would correspond to 2.58 standard errors or a Z star value of 2.58. These others, the 80%, the 99%, because these are sort of strange looking numbers, those don't come up when we do the empirical rule, but they follow the normal distribution. And so most of the time, we're not going to have to calculate these by hand. We're going to use StatCrunch to figure these out. But I want you to be familiar with at least the basics, like a 95% confidence level would correspond to a Z star value of 2, which means you're including 2 standard errors in your estimate. All right. How do we put this all together? Let's kind of formalize the formula here. So confidence intervals are often going to be in the form. So P hat plus or minus the margin of error. So whatever our margin of error is that we calculate back here, we're going to add and subtract that to our P hat value. So M is the margin of error. Since the margin of error is equal to Z star times the standard error, where standard error is, where SE is the standard error, if we put all this together, the confidence interval is built by doing P hat plus or minus Z star times the standard error, or the estimated standard error that we're going to use. So to find the standard error, we substitute P hat for P. Since P is unknown whenever we do a confidence interval, our estimated standard error is going to be equal to P hat times 1 minus P hat divided by N. So we're going to use P hat in place of P because we don't know what P hat is. Don't worry about this little EST. This little EST just stands for estimated standard error. If you want to put that in here, you can. It doesn't really matter. The point is to compute your standard error, you have to use p hat instead of p because we don't know what p is when we're doing a confidence interval. This formula looks more complicated than it is. We're going to do a couple of examples and you'll have this. It's not as bad as it looks. Quick comment here. Since the confidence interval calculations are based on the central limit theorem for sample proportions, the central limit theorem conditions that we talked about in the previous section, those 3 conditions still have to be satisfied. So what are those 3 conditions again? The sample has to be random and independent. The sample has to be large enough to expect at least 10 successes and 10 failures. The only difference now is instead of using p hat, or instead of using p, we have to use p hat to make that calculation, but it's the same idea. And then finally, the population needs to be large enough to be at least 10 times your sample size. Let's do an example here. During a recent semester, 63 of 159 students in MAT223 that were randomly surveyed indicated that they had had a negative situation occurred to them based on a social media posting. Let us estimate the percentage of all Flagler College students then who had a negative situation occur based on a social media posting. So we know from our sample, 63 out of 159 had this experience. We want to make an inference on how many of all of Flagler College students might have had a negative situation occur. This is similar to what you'd be doing in your project. So in your project, remember we came up with those research questions that you wanted to make an estimate about your population of all Flagler College students. One of the things you're going to do is create a confidence interval, and that's how you're going to make your estimate, where you said what proportion of all Flagler College students have had a negative situation occur based on social media posting. This is exactly what you're going to do in your project, so make sure this makes sense. Let's start by calculating what p hat is. So what percent of students surveyed, so surveyed would just be p hat. So p hat is going to be 63 out of 159. So that's the proportion from our survey. And I've got the percentage here that looks to me like that's about 0.396 approximately. Okay? What symbol do we use to represent the proportion that we calculated in part A? So that, of course, would be p hat. And since it's based on our sample, that's a sample statistic. Check that the conditions of the central limit theorem applied. Well, assuming it was a random sample, they told us it was. So yes, it's a random sample. Is it large enough to expect 10 successes and 10 failures? Well, we had 159 people surveyed. So the number of successes that we would expect would be n times p hat. So in this case, that would be n, which was 159, times p hat, which is 0.396. Now, we actually already have this number. That is the 63. That's exactly where that number came from, about 63, which is more than 10. So if they give you the number of successes, that's 63. That is the number of successes. There's nothing extra to calculate here. If they'd given it to me as a percentage, this is the procedure that I would have followed. And then, of course, the number of failures would be the complement of that. And I'm going to skip the details here, but it would be 159 minus the 63. Well, let me go ahead and give you the percentages just so you have it in your notes. If I do 1 minus p hat, so if p hat was that 0.396 number, the complement was 0.604. So that means we've got 159 times 0.604, which should be the rest of the students in my survey. So times 159. Oops, wait a minute. Sorry. 0.604 times 159 gives me about 96 students or so. So about 96 students said no, which is definitely more than 10. Is our population sufficiently large? Well, you got to think about your population. Your population is all of the students at Flagler College. So if my population, I think the population at Flagler College, ballpark, I don't know exactly how many students we have, but it's about 2,500 students. Is that at least 10 times our sample size? So your population needs to be at least 10 times your sample size. Well, my sample size was 159 students, so 10 times that would be 1,590. 2,500, of course, is more than that, so we are good to go. So yes, the conditions for the central limit theorem are satisfied. Let's go ahead and calculate our standard error. So our standard error, and this is an estimated standard error, but you don't have to write the EST if you don't want to. I just want you to remember we're estimating it using p hat. Okay, so that's going to be the square root of p hat times 1 minus p hat divided by n, which was, what was n? I believe it was 159. So let's go to our calculator and let's compute this number. So we've got 1 minus 0.396, 1 minus 0.396 times 0.396 divided by 159. And then we're going to take the square root of that, and we get I'm getting 0.0387. I'm going to round it to 0.039. 039 is going to be our standard error. All right, so the next part asks us to actually compute the confidence interval. So they want a 95% confidence interval. They have to tell you what confidence level to use. They'll say construct a 95% interval or a 90% interval or whatever they ask for in the question. What is the value of Z star? So if it's a 95% confidence interval, let's go back up to our chart. 95% confidence interval means my Z star value is going to be 2 right here. So Z star is going to be equal to 2. Calculate the margin of error. So the margin of error, remember, that is Z star times your standard error. Make sure you see where I'm getting these formulas from. Don't just blindly copy them down. Go back and look at your notes. The margin of error, remember, was Z star times your standard error. So Z star times my standard error means I'm going to do 2 times the standard error that I just computed right here, which was the 0.039. So 2 times 0.039 is 0.078. Find the lower bound for your confidence interval. So to get my lower bound, I'm going to do p hat minus the margin of error. So that's the notation I had back here where I said p hat plus or minus the margin of error. So p hat plus the margin of error gives me my upper bound. P hat minus the margin of error gives me my lower bound. So I'm going to do p hat minus the margin of error. So my p hat, I forgot what it was. P hat was 0.396. So it's going to be 0.396 minus 0.078 that I just computed. So let's get that number. So 0.396 minus 0.078, and I get a lower bound of 0.318. My upper bound, we're going to do the same thing, but we're going to add this time. We're going to add the margin of error. So it's the same numbers, 0.396 plus wait a minute. Let's see, 0.078 was my margin of error. So if we add it this time, so let's do that. We're going to do 0.396 plus 0.078. I get an upper bound of 0.474. Graph and label the confidence interval. So what they're asking me to say graph, it's nothing super formal. They just want you to do a quick little kind of like a number line. So in the middle, we've got p hat. So p hat goes right in the middle. So my p hat was 0.396. My lower bound, p hat minus m, was 0.318. And then my upper bound, p hat plus m, was 0.474. So interpret the confidence interval. Let's put this together. So we're going to write a statement, and we're going to say we are 95% confident. Now, what are we 95% confident about? We're talking about the percentage of all Flagler College students who had a negative situation occur based on social media. So we're 95% confident that the percent of all, I'm going to say Flagler College students who had a negative situation occur is between what two numbers? So my lower bound was here and my upper bound was here. You can write these as decimals or you can write them as percentages. It doesn't matter, whatever they ask for in the question. I'm going to use percentages. I think that sounds a little bit nicer. So I'm going to say it's between 31.8%, that's this number right here as a percentage, and the upper bound right here, 47.5%. 0.4%. So we don't know exactly how many Flagler College students had this situation. We think it's around this percentage. We think it's around 39.6%, give or take, but we think it's between 31.8% and 47.4%. So we're making an inference or an estimate for what we think is true about the population proportion. Okay, let's look at another example. According to Pew Research, a 2014 survey found that 32.1% of adults aged 18 to 34 were living with their parents. Suppose that this was based on a random sample of 1,200 adults in this age group. Okay? Check that the conditions of the central limit theorem apply. I'm going to go through this quickly because I really want to get to the StatCrunch example, and I think you probably get the idea of checking these. But they told us that it was a random sample, so we are good to go. It's large enough. It's got 1,200 people in it. I'm going to assume, well, I'm not assuming, it is large enough. It's a large enough sample that's certainly large enough for at least 10 successes and 10 failures based on this number here. And then the population would be all adults that are in this age range. So our population of all adults is certainly large enough. Our population is going to be more than 10 times the sample size. So we are good to go with the three conditions. Now it says use StatCrunch to find confidence intervals using levels of 80, 90, 95, and 99%. So let's talk about how to do this in StatCrunch. So in class, when you're asked to do this in StatCrunch, I want you to remember these instructions are right here. These are the steps that you're going to follow to calculate a confidence interval in StatCrunch. So let's go through an example of that here. So let me go back to StatCrunch. I think I have a window open here. Let me close this out. And I'm going to go to, it says stat and then proportion stats and then one sample with summary. So I'm going to go stat, proportion stats, one sample with summary. Now in StatCrunch, when you put these in, you have to put in the number of successes over the number of observations. So if they give you a percentage, you have to figure that out. In this example, let's see what they gave us. They told us that 32.1% of the people in their survey were living with their parents. So I can't put that percentage into StatCrunch. I have to put in the number. So let me go back and let me figure out what the number of successes, that's what it says. Enter the number of successes. This must be an integer. Use the percentage to figure this out if it's not given. So if my p hat was 32.1% and my sample size was 1,200, then the number of successes is going to be 0.321, so 32% of the 1,200 figure. So I need to get that number if they don't expressly give it to you. So I'm going to do 0.321 times 1,200, and I get 385.2. I'm going to round that to the nearest whole number, and I'm just going to say 385. Enter the number of observations. The number of observations is your sample size. How many people did we observe? That's going to be the number of observations. So I'm going to put in 385 out of 1,200 observations. So let's do that. 385 out of 1,200 observations. And then the next thing you're going to do is select confidence interval for P and then enter the appropriate confidence level. Oops, wrong button. So the hypothesis testing we're going to do later. This time we're going to do confidence interval. I'm going to start with a 95% confidence interval, and I'm going to click on, actually, you know what? I'm going to start with 80%. Let's do that one first. So I'm going to change this to 80%. I'm going to click on compute. Okay, here it is. So I want you to write these numbers in the table that follows on the next page. So an 80% confidence interval for this particular sample. The lower bound is right here, your lower limit. And your upper limit is what you want to focus on. So your lower limit is I'm going to use 4 decimals to write this out. So 0.3036 for my lower limit. So let's go to our table here. So I'm going to come back to the rest of this. My lower limit for the first one is 0.30. I think it was 36. I forgot what it was already. Let me go back to it. 0.3. Here it is. 0.3036. And then my upper limit is 0.3381. So 0.3381. Now, my table here, it's the same information that's in StatCrunch. I've just got the standard error on the end here. StatCrunch will compute the standard error for you. There's your standard error. So my standard error is 0.013. I'm going to just round it. So I'm going to put that here, 0.013. And my sample proportion, StatCrunch will also calculate, is 32%, 0.32. Really, it's 0.321. Let's fill that in, 0.321. We knew that. That was actually given to us in the original question, but StatCrunch will give us that number as well. Let's go ahead and do a 90% confidence interval. So same sample, same data. What I'm going to go to do is Options, Edit. I don't have to change any of these numbers because I'm dealing with the same sample, but I'm going to change this to a 90% interval, and let's look at the difference. Notice that the sample proportion does not change because the numbers for the sample, number of successes, did not change. The standard error does not change for the same reason. The sample size is exactly the same, so that did not change. But what did change is my lower limit and my upper limit. So now my lower limit is 0.299. Let's go ahead and write that in. So my lower limit is 0.299, and my upper limit is 0.343. And again, these other numbers will not change because my sample itself is exactly the same. So the sample proportion and the standard error have not been touched. What changes is the confidence level. And the reason that's changing is because that margin of error is going to get a little bit bigger with each one of these. So let's do 95% and look at the difference. So I'm going to go Options, Edit, and I'm going to change this now to a 95% interval. All right, so my lower limit is 0.294. So 0.294. My upper limit is 0.347. 0.347. Again, these other numbers are exactly the same. Nothing's changed. Actually, I can go ahead and fill this one in too because I'm not changing anything else. Let's do the 99% confidence interval and see what that looks like. So Options, Edit again. We're going to change this to 99%. And my lower limit is 0.286. Let's do that one, 0.286, and my upper limit is 0.356. So 0.356. So it says, what happened to the confidence interval as the confidence level increases? So what they mean by that is really what they're asking about is the interval width. So what I want you to notice here is how wide did each of these get? So the width for each of these, let's do this. Let's do a quick calculation of the width for each of these. So literally, I mean how wide, what is the distance between the lower limit and the upper limit? So for the first one, I'm going to do 0.3381 minus 0.3036, and I get a width for that first interval of 0.0345. So I want you to see what I'm doing. All I'm doing is subtracting the upper limit minus the lower limit. That's all I did to get that number. Let's do the next one. I'm going to do 0.343 minus 0.299, and I'm getting a width of 0.044. The next one, I'm going to do 0.347 minus 0.294, and I'm getting a width of 0.053. And then the last one, we've got 0.356 minus 0.286, and I'm getting a width of 0.07. So what I want you to observe here is what's happened. As the confidence level goes up, notice what happens to the width. The width also got wider. So as the confidence level increases, the width also increases. So the higher the confidence, the wider the interval. And that's going to be the case every time. Is it plausible to conclude that the true percentage of adults living with their parents in this age group is 38%? So if you look at all of your confidence intervals, did any of the intervals, this is what I want you to ask yourself, did any of these intervals include 38%? The first one, the highest value is 0.33. The next one, the highest value is 0.34. The highest we got was 0.356. So did any of these include the 38%? No, they did not. Therefore, I would say it is not plausible. So we can say since none of the intervals, let's say captured the 38%. So since none of these included 38%, I would say no, that number is not plausible. Just kind of summarize what we just said. As the confidence level increases, the width of the confidence level also increases. Okay, let's do another example here. It says a political consultant randomly surveys 500 voters in a district to see how many intend to vote for a certain candidate. Of the 500 voters, 265 indicated that they will vote for the candidate. So let's write a few things down here. N is equal to 500, and then P hat, we're going to have to compute that in a second. That's going to be the 265 out of the 500 that we surveyed. So it says use a 99% confidence interval to decide if the consultant should predict whether or not the candidate will win the election. Verify the central limit theorem is met. I'm going to skip this part for now. I think you got the hang of it. We've got a very large sample here, so I think we're probably okay. Let's go ahead and actually compute the confidence interval, and I'm going to do this by hand just for practice. The first thing that we need to figure out is the standard error. I always like to start with that. So let's compute our standard error. It's going to be, well, before I do that, let me get this as a percentage. That'll make it a little bit easier to write things out. So I'm going to do 265 divided by 500. So my P hat is 53%. So my standard error is going to be 53% times 1 minus the 53% divided by N, which is 500. So let me see. I think I have that number. I'm going to skip the details here, and I'm just going to put that in my calculator and tell you that that number is 0.02, let's say 0.22. All right. So the next thing I need to know to compute the confidence interval is I need to know what Z star value to use. So if they're asking me for a 99% confidence interval, let me go back up here to my chart and find the Z star value that corresponds to a 99% confidence interval. Here it is, 99% confidence interval. The Z star value that I need to use is 2.58. So let's include that. So my Z star value is going to be 2.58. So then let's go ahead and compute the margin of error. So the margin of error, remember, is Z star times the standard error that you computed. So that's going to be 2.58 times the standard error of 0.022. And I'm getting a Z star value of, let's see what we have, 2.58 times 0.022. I'm getting a margin of error of 0.05, let's say 0.57. We'll round that and say 0.57. All right, so to calculate my confidence interval, I'm going to do P hat plus and minus the margin of error. So my lower bound, P hat minus the margin of error, is going to be the 0.53 number minus the 0.057 that I just computed. So that's going to be 0.53 minus 0.057, and I'm getting 0.473. My upper bound is P hat plus the margin of error, so that's going to be 0.53 plus 0.057. And so that number, let's see what that gives us, 0.53 plus 0.057, I'm getting 0.587. All right, so my confidence interval, there's a couple of different ways we can write this. One way to write this is using interval notation, just like you learned back in high school algebra. Interval notation with a parentheses. My lower bound is 0.473. My upper bound is 0.587. So there's my basic confidence interval. So somewhere between 0.473 and 0.587% of the population we think is going to vote for this particular candidate. So let's summarize our results. Let's write a statement. We can say we are 99% confident that between 47.3%, so that's this number just as a percentage, and 58.7%, so again, that's this number as a percentage, will vote for the candidate. Okay, so let's go back to the question. The question was, should the political consultant be confident that he will win the election? He must obtain a simple majority of the votes. So in other words, the candidate must get more than 50% to win the election. Well, I would say no, he should not be confident. The reason I say that is because part of this interval drops below 50%. You see the lower bound is below 50%. The lower bound is 47%. So for that reason, I would say no, he should not be confident. Let me phrase it how they said. They said, should he predict? Let's use that term. So he should not predict a win. And the reason we'll say is since the lower bound drops below the 50% that he would need for the win. And so that's what you want to look at. If they're looking for a majority, if any of it drops below 50%, then I would say no, we cannot predict a majority based on that. It's just as likely that it could be below 50% as it could, well, maybe not, I shouldn't say that, but there is a good chance that it could be below 50% as well as above 50%. So I don't think he can decide that based on this interval. If the entire interval had been above 50%, then I would say, yeah, he can make that prediction that his candidate's going to win, but that wasn't the case here. All right, let's do this last example. According to housingwire.com, 93.8% of homeowners had positive equity in their homes. Suppose that the margin of sampling error is plus or minus 3 percentage points. You might have heard that term before. When somebody talks about a survey, a lot of times around election time, they'll say the margin of error is plus or minus 3 percentage points. This is exactly what they're talking about. The margin of error is 3 percentage points, and they use a confidence interval, a confidence level of 95%. State the confidence interval in notation. Remember that the confidence interval is p hat plus or minus the margin of error. If they give you the margin of error, this is actually a really easy question to answer. All I'm going to do is take the p hat value. So the p hat is going to be the 93.8%. And this question, I don't love the way this question is worded because 93.8% doesn't come from a sample, but 93% we're assuming is what they got from some sort of a survey that they conducted. So we're assuming they conducted a survey. 93.8% said that they had positive equity in their homes. So we'll assume that's our p hat value. So to get my confidence interval, I'm going to do that 93.8% plus or minus the margin of error of 3%. I wrote the same thing twice. Hold on. Let's see. So I'm going to do 93.8% plus or minus 3%. So 93.8% minus 3% would give me a lower bound of 95.5% and an upper bound of 90. Wait a second. I'm sorry. Hold on. Trying to do too many things at once here. Let me write this out so you can see what I'm doing. So we're going to do 93.8% minus the 3% puts me at 90.8% for my lower bound. 93.8% plus the 3% puts me at 96.8%. So we could say we are 95% confident. If we were keep to pulling sample after sample after sample after sample, 95% of our samples, we would find that 95% of the time they would capture the true population mean. So we are 95% confident that the proportion of all homeowners with positive equity, the real proportion is somewhere between 90.8% and 96.8%. So the next question is, how would you interpret that? I think I actually answered it. That's your interpretation. But the confidence interval notation-wise, we might write this using parentheses. So we might say 90.8 is my lower bound and 96.8% is my upper bound. So the big takeaway here I want you to remember is that we use these confidence intervals to estimate a population proportion. So we think the population proportion of all homeowners with positive equity is somewhere between this 90.8 and this 96.8% number.